All right, let's start. So yesterday we were discussing the following example. We had uh, stated this theorem, which says that a sequence is, if it is both bounded and monotonic, then it is convergent, right? And this is a picture where this monotonic sequence is, let's say, increasing, and it's bounded from above by some real number k. Then this sequence is increasing, but it will not go above this level. Therefore, it has to accumulate somewhere. And there is always such a number L, so that this sequence is convergent. And that is actually a property of real number system, completeness property of real number systems. Whenever you have an accumulation of points, then there is a limit point there. Okay, that's the property. That's a property of real numbers. And using this result, we want to show that this sequence defined by the recursive relation, where a1 is 1 and an is sorry. Okay. Okay. An plus 1 is square root of 6 plus an is convergent. That's what we want to show. So we just want to show that this is monotonic and bounded. To show that it is monotonic, we write down couple terms of the sequence, and we see that it's increasing, and then we prove it using induction. So we want to show that an plus 1 is larger than an. For n equals 1, a2 is larger than a1 because a2 is this sequence, this term, a1 is this, and square root of 7 is clearly larger than 1. And then for induction, we assume that the nth plus first term is larger than n, and then using that, we would like to show that n plus second term is larger than an plus 1. And how can we do this? We write down an plus 2, that is square root of 6 plus an plus 1. But this an plus 1 is larger than by an by the assumption. Therefore, if I replace this an plus 1 by an, I get something smaller. But this is just an plus 1, so an plus 2 is larger than an plus 1. So that's the proof that an is increasing. And then we claim that an is between 1 and 3, always. Again, we use induction. For n equals 1, a1 is just 1, so it is between 1 and 3. And then we assume that an is between 1 and 3. And then we would like to show that an plus 1 satisfies the same relation. And then we do what? Well, an plus 1 is 6 plus an, and this an is at least 1. Therefore, this is at least 7. Therefore, this term is greater than or equal to square root of 7, which is larger than 1. But in particular, but also an is less than 3. Therefore, 6 plus an is less than 6 plus 3, which is 9. And square root of 9 is just 3. Therefore, an plus 1 is less than 3. So that proves that an is both increasing and monotonic. In particular, it is convergent. Now we would like to find out, since it is convergent, what is the limit, okay? What is the limit of this sequence? And then there we use, again, the relation. Well, we have this relation, 6 plus an. We take limit of both sides, okay? Limit of an plus 1 limit of 6 plus an. Well, if an goes to somewhere, then an plus 1 will go to the same place, right? Because I mean it is the same sequence, just one unit shifted, right? So the limit of this, if this limit, let's say L, okay, and we would like to find out this L, the limit of this thing is the same as that one. So this is L. What about this one? Well, you see here 6 plus square root of a, I can write this. F of x is, let's say, 6 plus x. This is a continuous function, and its limit as x goes to L of f of x is just 6 plus L, since it is continuous. In particular, as n goes to infinity, f of an, well, an goes to L, so this is the same thing uh, as x goes to L of f of x, because an goes to L, and this is just uh, 6 plus L. Therefore, this limit is just square root of 6 plus L. So we obtain the following identity then. Square root of 6 is L is the same as square root of 6 plus L. Well, then I have an algebraic equation here, right? So from this, we obtain this algebraic equation. We can just solve this by squaring both sides. L squared is just square of this, which is 6 plus L. And from this, we get L squared minus L minus 6 is 0. That is L minus 3, L plus 2 equals 0. So, sorry. So, L is either 3 or L equals minus 2. Well, one thing we know is the following. Uh, ANs are always larger than 1, right? Therefore, its limit will be larger than or equal to 1. Ee, Sanırım bu kalemin de pili bitti. So L is larger than 1 because since AN is always larger than 1, sorry, its limit is larger than 1. Since L is larger than 1, this is not possible. So L cannot be 2 since L is larger than or equal to 1. Hence, the limit L, limit of AN, which is L, must be 3. Okay? All right. Okay. There is another example. So I have 1 plus 1 over n to the power n, and from so this is the sequence. So we are asked to find the limit of this. Well, the limit of this is what? I guess you have seen this kind of limits in 119, right? We had known, we know this, we know the following. So if you have this sequence, not sequence, the function 1 plus 1 over x, and as x goes to infinity, this is the same as this one. Here n takes only integer values, but here x takes any values. But we know that this function has limit at infinity, and that limit is equal to e, right? So if your uh, sequence is given by a function like this one, and if this function has limit at infinity, then your sequence has a limit at infinity as n goes to infinity, and that's just the limit of the function at infinity. Therefore, this sequence is just is convergent to the number e, because f of x 1 plus 1 over x uh, uh, has limit as n goes to infinity, which is equal to e. Okay, we have some facts which will be useful. Let me state them. If an, let's say, is ultimately increasing, then it is either bounded above and therefore convergent, convergent, or it is not bounded and diverges to infinity, right? If you have a sequence which is increasing, if it is not bounded, then it will go to infinity, right? So it is divergent to infinity. If it is bounded, then by the previous theorem, it is convergent to some real number, okay? So that's just the statement of that fact. If you have any questions about these things, just stop me and ask, okay? Yani bir dizi e, artansa ya yukarıdan sınırlıdır. Sınırlıysa zaten convergent olduğunu biliyoruz. Sınırsızsa da bu ne demek? Giderek daha yüksek değerler alıyor, değil mi? Sizin seçtiğiniz her sayıdan daha yükseğe çıkıyor. Demek ki sonsuza gidiyor. Bu da onu söylüyor. Alright, so another theorem is the following. It has two parts. If x is larger than 1 in absolute value, then no, sorry, less than 1. I am sorry, less than 1. Then limit of xn is 0. This is something you already know, right? If x is any real number, then limit x to the power n divided by n factorial is always 0, okay? No matter what x is, okay? For each x, x to the power n divided by n factorial is 0, meaning that n factorial grows much faster than x to the power n. Okay, that's why the ratio has limit 0. And let's see the proof of this. Since it is using several different facts. It's a nice example. Okay, for part A, uh, first observe that limit of as n goes to infinity uh, logarithm of x to the power in absolute value n. What is this limit? Well, uh, here of course we assume that if x is not 0. If x is 0, then of course, logarithm of 0 doesn't make sense. But in that case, if x is 0, 0 to the power n is 0, therefore limit is 0. So without loss of generality, we may assume that x is not 0. If x is not 0, then absolute value of x is positive. So I can write this. And then we know that this is just n times ln x. But this thing is less than 1. Logarithm of a real number which is less than 1 and a positive number which is less than 1 is a negative number. So this thing is a negative number. And then you multiply this negative number by n and you let n go to infinity. So you have a negative number, you multiply by 2, by 3, by 4, and so on. Of course, this will go to minus infinity. All right. So this limit is minus infinity. But then we have the following. Okay. Since f of x, which is e to the power x, is continuous and okay. And limit as x goes to minus infinity, e to the power x is 0, right? Why is that? You remember from, again, first semester calculus course, e to the power x has such a graph, right? So something like this. This is 1, x-axis, y-axis, and this is y equals f of x, which is e to the power x. So as x goes to minus infinity, e to the power x goes to 0. But then, now, I can write this. Limit as x goes to, sorry, as n goes to infinity, x to the power n, and this is just limit as n goes to infinity, e to the power logarithm of x to the power n. Why this is true? Why is this true? Because exponential and logarithm functions are inverse of each other. If you have a positive number, if you take its logarithm, and then if you take the exponential of the logarithm, you will get back to the number you started with. Therefore, logarithm of x to the power n above in the exponent of e is just x to the power n. But as n goes to infinity, we showed that as n goes to infinity, this thing goes to minus infinity. Therefore, right, as n goes to infinity, this gadget goes to minus infinity. So this is the same thing as this. Let's say r, okay, and r going to minus infinity, but this is just 0, right? So limit of x to the power n is 0. Okay. What about part B? What was part B? part B was this. If x is any real number, then this ratio has limit 0. Okay. Let's see why this is true. Okay. Maybe one more line here. So here we show that absolute value of xn is 0, but then we have this. Finally, maybe I should write one more line. Minus, you see, x to the power n is less than minus 1 times x to the power n is less than this, and this is less than x to the power n. And we showed that, no, I don't want this. Okay, yeah, we have this. We showed that this is convergent to 0 as n goes to infinity. Well, this is just the same thing multiplied with minus 1. So it will converge to minus 0, which is just 0 as n goes to infinity. Therefore, the guy in the middle has to converge to 0, right? So limit x to the power n is 0 by the uh, sandwich or squeezing lemma, by the squeeze theorem. Okay. For part B, remember that we have to prove the following. X to the power n divided by n is equal to 0 for any x, okay, real number. Let's see why this is true. Okay, now given x real number, choose some integer n so that uh, n is larger than absolute value of x, right? No matter what x is, once you give me a real number, I can always find an integer larger than that real number. So let's fix that real number, one of them. There are, of course, many integers larger than absolute value of x. I just fix one of them. Then we have the following. Now, if n is any other integer larger than this, then we have what? Let's see. Absolute value of x to the power n times n factorial. Well, this is what? This is just x is multiplied with itself n times. So this is just x. And then this is n factorial. So it is just 1 times 2 times 3 up to where? Somewhere here I will have x n, and then finally I have x and then little n, because I have n, small n is larger than big N. Therefore, since I have n factorial here, I will go from 1 up to n, and here I have exactly n many absolute values of x. All right, then we do what? Well, look at this gadget here. First terms here, x to the power n, so just this part, divided by n factorial, okay? And then what else do we have? I have x to the power n minus big N, and then here I have what? N plus 1 up to n, right? Okay. All right. So we have Okay. I can write the following. This is less than, yeah, this is less than the following. Ee, Şöyle yapayım aslında. N-1'e kadar gidelim. Şöyle diyeyim, pardon. Let me just go up to n minus 1, and then I have n plus 1, and then this. Okay, first I'll do this. I have n minus, I take the first n minus 1 terms, this gadgets, and here I have the denominators gives me n minus 1 factorial, and then I have x to the power absolute value of x divided by n, and then I have absolute value of x divided by n plus 1. If I replace n plus 1 by n, I will get something larger, right? Because I write something smaller in the denominator, so I get something larger. That's why I have inequality here. And then the next term is x, absolute value of x divided by n plus 2, but instead of n plus 2, I write n so that I get something larger. And I'll go up to the last term. Here I have absolute value of x divided by n, but I replace by big N so that I get again something larger. And how many terms do I have here? I have here we have small n terms, and here I have n minus 1 terms, so this is n minus 1 terms, which is just n plus 1 minus n terms, right? So what is this? Absolute value of x to the power n minus 1 factorial, and here I have absolute value of x divided by n to the power n plus 1 minus n. Okay. All right. Now you see x is a fixed number, and n, this big N is a fixed number, right? I fixed this n, big N, so that it is larger than absolute value of x. But the thing is that this is independent of small n. There is no small n here. So this is a this thing is a fixed number. I can call it, let's say, k. Okay, k times, and this is just, let's say, r to the power n plus 1 minus n, where k is this fixed number and r is the following number, which is absolute value of x divided by n. But remember that n was chosen so that n is larger than absolute value of x. Since n is larger than absolute value of x, r is less than 1. Okay? And we have what? I have this fixed number. So we have, okay, limit of x to the power n divided by n factorial is less than k, some fixed number, times r to the power uh, n plus 1 minus n, right? And I can write it this way, this gadget. This is r, so k times, sorry, k times uh, r to the power minus n times or n plus 1 and then r to the power n. Okay. Now this thing is also a fixed real number because r is a fixed number and big N is a fixed number. So this is a fixed number. Let me call it k prime times r to the power n. And r is less than 1 and greater than 0. Well, if you let n go to infinity, of course, this k prime will converge to k prime. It's a fixed number, but this thing will go to 0 as n goes to infinity. Therefore, this limit, which is always whatever it is, it should be positive. It shouldn't be negative because I have positive terms here. These are all positive, so limit, if it exists, it has to be positive. And this is 0. So again, by the squeezing theorem, right, this limit is squeezed by 0 from both sides. This implies that limit x to the power n divided by n factorial is 0. Okay, so that finishes the proof. Okay, any questions? Peki, bir tane, let's do one example related to this. Let's compute this limit as n goes to infinity. 3 to the power n, 4 to the power n, 5 to the power n divided by 5 to the power n. Well, this can be written like this. So here, this is just 3 over 5 to the power n, 4 over 5 to the power n, and then plus 1. Well, this is r to the power n, and r is less than 1, right? So this is 3 over 5 is less than 1. Therefore, its limit is 0. So that's the part A of this theorem, right? Part A of this theorem. If x is less than 1 in absolute value, then its nth power has limit 0 as n goes to infinity. Therefore, this thing has limit 0. This thing has limit 0. And this is constant terms. It is 1. Therefore, this limit is equal to 1. Okay, and 0, 4 over 5 is less than 1. So we have this. Okay. There are several exercises at the end of this section. Okay. And yesterday I sent you the syllabus. In the syllabus, there are suggested problems. Okay. You should work on those problems. And if you cannot solve them, then you should work more. And if you cannot do it again, then you should ask for help. Okay. Okay. Yeah. I can also hold maybe office hours on Fridays, maybe. Okay. The next topic is so-called infinite series. Okay. What's an infinite series? It's a formal sum. Formal sum means it's just a bunch of symbols and it doesn't have maybe a meaning till you define what it means. So let me just write down an infinite series uh, usually denoted as like this is a formal sum uh, of infinitely many terms. Okay. Uh, so this means a1 plus a2 plus a3 plus and so on. So it's a formal sum, meaning that this sum doesn't have to be equal to a real number or anything. Okay, it's just a sum of numbers. Uh, it's just a notation. So for example, 1 plus 2 plus 3 plus till infinity. This thing doesn't have a meaning, right? It is not convergent, but it's a series. It's a formal object. Okay, it's a formal object. Okay. Sometimes, usually we actually write the summation from not 1 but 0. Uh, we will mostly uh, consider series starting from n equals 0, uh, but in general uh, it can start from any integer. So I can consider a series like this, minus 2 to infinity an, or n equals 5 to infinity an. Okay, we may consider series like this also, but usually actually we write from 0 to infinity, but this book usually takes from 1 to infinity. All right, now we have a concept relating to series, sequence of partial sums. So if an, let's say from so an summation from 1 to infinity an is a series, its sequence of partial sums is defined as follows. So this is a sequence, and it is defined as follows. So it is the sequence Sn, where S1 is just the first term of the sequence. S2 is A1 plus A2. Okay. S3 is A1 plus A2 plus A3. And it goes like this. The nth term of this sequence is the sum of the first n terms of the series. Okay. This is a formal object, this summation. And from this formal object, I write down a sequence of partial sums. Why we call it partial sums? Because you take the first n terms, you add them up, so you take a partial sum, okay, of that infinite summation, and it goes like this. Now, this is a sequence of real numbers, right? This Sn is a sequence of real numbers, and we can talk about uh, all the concepts we have defined for sequences, like whether it is increasing, decreasing, bounded, or convergent, right? This Sn. Uh, and here is the definition. Okay, so this is convergence of a series. Convergence of a series is defined using the convergence of the uh, sequence of partial sums. We already know what uh, convergence of a sequence means, and using that we define convergence of series. Okay, here's the definition. Yeah, well, series right now doesn't have any meaning. It is an object like this. Okay, a series is like this. ANs are some numbers. AN is a sequence. I just add the terms of this. But this thing by itself so far has no meaning. It's a formal object, okay? But sequence is, this. It's a sequence of numbers, okay? From this series, we built up a sequence called the sequence of partial sums. And then using that sequence of partial sums, I define convergence of a series and so on. Okay, and that's what I will do now. Okay, we say that the series n from 1 to infinity an converges to the sum s, and we write this, and from 1 to infinity an equals s, if limit of Sn's, this sequence of partial sums is convergent to S, okay? Where Sn is the nth partial sum of the series. So meaning that Sn is just A1, A2 up to An, okay? So the convergence of a series is defined by means of convergence of a sequence. Which sequence? The sequence of partial sums. Okay. All right. Let's see. Okay, geometric series, for example. So that's an example of a series. Okay. Uh, consider a series of the form uh, a times r to the power n minus 1 and from 1 to infinity, where uh, a and r are real numbers. Okay. Uh, this is the series. Uh, note that if we let a n to be just a times r to the power n minus 1, then this series is just this series an. Now let's study whether this is convergent or not. Okay, how can we do this? So convergence. Well, what's the definition? One should write down its uh, sequence of partial sums. Sequence of partial sums So what is uh, okay? S1. S1 is just A1, and A1 is just uh, A1 is just A times R to the power, right? AN is just A times R to the power n minus 1. So A1 is just A times R to the power 0, which is just A. What is S2? Uh, it is A1 plus A2. So it is A1 is just A2 is just A times R to the power 2 minus 1, which is 1. What about S3? It is A1 plus A2 plus A3. So it is A times A plus R, A times R, A times R squared, right? Goes like this. Sn is just A1 up to A2 up to AN. So it is A plus AR squared plus AR to the power n minus 1. So to check the convergence of this series, I have to check the convergence of this sequence, right? So we ask this: is this limit exist? Okay, uh, does this limit exist? So that's the problem. How can we do this? Uh, so, uh, well, let's write down an in this way. So this is a times 1 plus r squared r to the power n minus 1. And I can write this as follows: Sn is equal to this. And this is just, you see, this is just 1 minus r to the power n divided by 1 minus r. Okay. Why is that? Because since 1 minus r times 1 plus r to the power n minus 1 is just 1 minus r to the power n. Just multiply this out, you will get this, okay? So instead of this expression, I can write 1 minus r to the power n divided by 1 minus r. Then what? Well, then you see, uh, this can be written as 8 over 1 minus r, and then I have here 1 minus r to the power n. Of course, here, you have to be careful. You assume that r is not 1. And then I'll come back and see what happens if r is equal to 1. But for this computation, I shouldn't let r equal to 1, right? Because then I would divide by 0. That's not allowed. All right. Then what? Well, I am interested in the limit of this. When I take n, if I take n, to infinity, well, this term here is a real number. A is a real number, R is a real number, not 1, not equal to 1. So A over 1 minus R is a real number. And then I take limit of this expression. Limit of 1 is just 1, and limit of R to the power n. And we know that R to the power n, it is, if R is less than 1 in absolute value, it is 0, right? So if R is less than 1, then limit of R to the power n is 0. That's the part A of the theorem we proved in the beginning of the lecture, as n goes to infinity, so that limit Sn as n goes to infinity is just limit as n goes to infinity. This is A over 1 minus r to the power n. This is a fixed number. I can just take it outside the limit. This has limit 1 and this has limit 0. So I have 1 minus 0. So the limit is 1 minus r. In particular, this is convergent. So if r is less than 1, then this Sn is convergent. Sn is convergent means that the series is convergent and equals S, equals this limit value. Then the sequence Sn is convergent with limit A over 1 minus r, so that the series, right, by definition of convergence of a series, the series A times r to the power n is convergent, and this sum, so the limit is just A over 1 minus r. Okay, so the sum is equal to this number. What about the other cases? If r equals 1, then of course this gadget r to the power n is just, r is 1, therefore this is just this. So you just keep adding a by itself, right? Infinitely many times. So this is just a plus a plus a infinitely many times. So in this case, the nth partial sum Sn will be what? It is just S1 is the first term, S2 is the sum of the first two terms, and then this is S3 and so on. So Sn is just the sum of the first n terms. So you add a n times with itself, n terms. So this is n times a. And what is the limit of this? This limit is, if so a is 0, then this is 0 if a is 0. But if a is positive, then it is divergent to plus infinity. And if a is negative, then it's of course minus infinity. So it is convergent only if a is 0. Okay, it is convergent, hence this is convergent convergent only if a is 0. And in that case, limit is of course 0. If r is larger than 1, then uh, r to the power n, of course, goes to infinity as n goes to infinity, right? Because you have a number larger than 1, you just keep multiplying with itself. It's the exponential sequence and it will converge to infinity. Uh, so, for example, you know, 3 to the power n, right? Okay. So that Sn, which is just r, a times a to the power r to the power n minus 1 will go to infinity. If r is less than minus 1, then r to the power n will go to will oscillate between minus infinity and plus infinity actually. Then again r to the power n is divergent. For example, consider r equals minus 3, then r to the power n is this sequence. For n equals 1, you have minus 3 and then 9, minus 27, 81, minus this, and then plus something. So the values will get bigger and bigger in both ways, in positive and negative ways. So it is not convergent. Okay. Not convergent. It's divergent. Okay. So as a result, we have the following. As a result, beni uyarmadınız. Zaman geçmiş. Neyse şöyle yapayım da şunu bitireyim. So this is converges to 0 if a is 0. Converges to a over 1 minus r if absolute value of r is less than 1. Diverges to infinity if r is larger than or equal to 1 and a positive. Diverges to minus infinity if r is larger than 1 and a is negative, and diverges if r less than minus 1 and a is not 0. Okay, so it is convergent only if r is less than 1 in absolute value or if a is 0. Okay. All right, let's have a break. After the break, we may continue.